Good afternoon, CS109. How are you guys doing today? Fantastic. That's what I love to hear. It's Friday, so as you guys are coming in, I'll tell you a quick story. I don't believe I've told you the story of how my grandparents ended up in the US. Okay, let me tell you, it's an interesting story. This is on my mom's side. So my grandmother was living in a country called Belgium, and this is the story of how she ended up in New York, which is where she met my grandfather. So she was living in Belgium, in a city called Brussels, and she was living there just before World War II broke out. And she was about 17 years old when she was living there. And that side of my family was Jewish, so they're Jewish living in Belgium. And as you can imagine, that was a bad time to be in Europe. And at some point, her father had to do some business in Germany. And he went there and he was like, oh, this is about to get very, very, very serious. So as soon as he got back to Belgium, he started selling all his things. And he didn't know how to drive, but they purchased a car. And then when the Germans invaded that part of Europe, they just left. They were a couple days ahead of what we now call the Blitzkrieg, and they made it all the way to France. And when we got to France, they're technically Dutch citizens, so the Queen of Holland had set up 5 boats, and they got on one of those boats to go to the UK, 4 of which were sunk by U-boats, and they make it to London just in time for the London Blitz. And then they managed to survive that too, and then get on a boat that takes them all the way to New York, where she meets my grandfather, and then they fall in love, and that was an important part of my story. Another bit of fruit of the random tree. Speaking of randomness, today we are going to be learning about adding random variables, which sounds a little bit dry, but we're in this part of CS109 where we're learning about deep theory, and this is one of the introductions into thinking about one of the most beautiful results in all of probability history. And if we play our cards right today, we will get to see that most gorgeous result in the world of theory in probability. So that's what we're going to be talking about. Before we jump in though, I did want to tell you guys about one of my favorite parts of CS109. I'll be putting more details about this up after class, but I want to announce it for the first time today. As you may or may not know, one of my favorite things to do in CS109 is to host what I call a personal challenge. And a personal challenge goes like this. There are so many ways that you could show me that you understand the material in the class. Midterm is one of them, but for some people, exam is not the best way. And on the other hand, one of my favorite things while learning is to give people space to be curious, to be creative, and to express themselves in the language of what they've just learned. To that extent, we host this personal challenge. You get to do anything of interest in the context of what we've learned in class. So maybe you thought what we learned in class was really relevant to something in your life and you want to create something and explore some topic more deeply, you could do a personal challenge. You'll submit a short write-up and or a little YouTube video, and then we'll give you some extra credit. Now, this is optional in the deepest sense of the word optional. Let me give you my guarantee. If you don't participate in this optional personal challenge, your grade walking out of CS109 will be the same as if this challenge never existed. So this is not like extra credit which is going to change the curve. It's extra credit that makes it optional in the truest sense of the word optional. But if you do this and you're able to show that you understand this material, and maybe you show that you understand the material perhaps even better than an exam, then we'll be giving you extra credit too that will help your grade. Does that make sense? This guarantee of optional in the truest sense of the word optional? I hate when an extra credit and you're like, I kind of have to do it, don't I? And this is not one of those. But I do hope you participate because I think it's just a beautiful way to explore the material more deeply in a way that's very personal to you and that can make it relevant to your life. I did want to show you guys some examples. Here's one example of what somebody made a few years back. Somebody, for their project, made the No Humans Allowed Club. And the way this works is you have to enter 50 random numbers and it tells you if you're a computer or a human. So I'm going to start entering some numbers. Oh, I don't know. I'm getting there. It's definitely going to think I'm a robot because these are completely random. And it says, I've figured out that you are in fact a human, like the reverse CAPTCHA. We thought that was quite nice and showed some nice understanding of the material. One person was really interested in the topic that we're going to teach today in class, And they want to understand something that I said quickly. I said, we're going to use this result, but we're not going to prove it in CS109. She really wanted to understand the proof. So she went deep and understood the proof, and then made a YouTube video to teach other people the proof. And we thought that this showed incredible understanding of nuance of CS109. And you guys remember, we talked about flipping frisbees and how a student showed how the way people start ultimate frisbee games is unfair. She then came up with another algorithm. She also modeled these as beta distributions and went in the field, did a lot of experiments, and gave probability distributions over how likely a frisbee is to actually be a heads. All good things. So there's so many ways to combine what you find interesting with probability. This is not supposed to be a representative sample. Instead, it's just supposed to spark some creativity and excitement in you guys. So there you have it, the optional challenge, a personal challenge. You're not competing against other people. Though you're not competing against people, the TAs will take a look, and we always will find some that just make us so excited, we give some sort of really nice reward to them. Okay, any questions about logistics before we jump into things? We haven't graded midterms, that will happen this weekend, so you'll hear more about that on Monday. Questions, concerns, thoughts? Okay, let's start out with a new definition. So on Wednesday's class, we learned about beta distributions, and those were very beautiful, but today we're going to shift gears into just thinking about what happens when we add random variables. But we need to start with a new piece of terminology that you might have seen before, but in case you hadn't, I want you to know it, live it, learn it, love it, because we'll see it a lot in the rest of CS109. IID. IID stands for independent and identically distributed. And you'll start seeing this a lot. It's very common in the world of data science and machine learning. You'll often say, I have a bunch of random variables, and then you'll see a claim, and these random variables are IID. It's a stronger claim than just saying they're independent. IID includes that they're independent, but it also means that they're identically distributed. Identically distributed is just terminology for saying that if they're discrete, all of their probability mass functions are the same. If they're continuous, all their probability density functions are the same. As such, because if all these things are the same, you must have the same expectation, you must have the same variance. Does this mean that all the random variables are the same? No, they're not going to be the same number. They're just going to be pulled from the same distribution. Let's take this out for a spin. I'm going to give you a few different contexts, and I want you to think about whether or not they're IID. So, first one. We're going to say there's n random variables, x1 through xn. xi is an exponential with a particular lambda. And I'm going to then claim that all xi's are independent. So are these independent and identically distributed? Okay, why don't you look at this list? We've got the first one that says, xi's are all exponentials and they're all independent. The second one, the only difference is that there's a little subscript I, which means that each xi has its own lambda. And then the third one, we say that x1 is equal to x2 is equal to xn. And the last one, we say that xi all come from binomials, each with different number of trials, but the same probability p. And then we claim that they're all independent. So talk about with the person next to you, a little bit warm up for CS109 on a Friday. Which of these are IID, independent and identically distributed? Okay, go, talk, have a good little chat, and then we'll talk about this all together. We're going to do a ruckus vote by loudness. There's no wrong answer here, This is just practice. Okay, we're going to yell the first one. IID or not IID. Let's say yes for IID, no for not IID. Let's just yell.
Yes.
Okay, Fantastic. The first one is IID. And this makes sense because are they independent? Well, we've said they're all independent. And are they identically distributed? Yeah, they're all have the exact same probability density function because they're all exponentials with the same lambda. Thus, if you were to plot all of their probability density functions, they would have the same curve. They won't be the same values, but they have the same distribution. So IID. How about this one? A little cheeky? No. Why not? It looks so independent, and it looks so identically distributed. The PDFs are different. Why are the PDFs different? They're all exponentials. Oh yeah, if you have different lambdas, you'll have different PDFs. That's actually a different distribution. So even though it's the same distribution family, because they have different lambdas, it won't be the exact same curve. So since the lambda i's assumed are not equal, these are not identically distributed. Okay, how about the third one? No. Feels interesting, right? They're definitely identically distributed, but are they independent? Independent would mean knowing one gives you no information about the other ones. And if I tell you one, you now know complete information about the other one. So in fact, these don't fit that new terminology definition. And this is a little bit cheeky, but how about this last one? Let's take it on home. No, yeah, because even though they have the same parameter p, and even though they're all independent, you need the whole probability mass function to be the same, and because n is different, they will in fact be different distributions. Unless, of course, all the ni's happen to be equal. Okay, so then I leave us with this first question to start our day. We're going into this theoretical part of CS109, and we've talked about random variables. We've talked about conditional beliefs of random variables, conditioned on observing things. But one thing that seems like it would be interesting to do is thinking about what happens when we apply mathematical functions to random variables. And the simplest one to start out with is addition. What happens if you take one random variable and add another random variable? Recall that each random variable is going to take on a value. So if I say something like, x plus y, that's what I mean when that's x plus 5. If I do x plus y, that's what I mean when I talk about adding random variables. No matter what, we imagine these to be numbers that take on values probabilistically. So it'll be this x's number plus this y's number. But the result won't be deterministic. The result of adding these two numbers will depend on what value x takes and what value y takes. And I do want to explain a little bit why you should care. And there's a whole bunch of reasons why we could just care about addition. For example, at some point we talked about zero-sum games. We talked about the probability that the Warriors would win. And we ended up with, in the world of this thing called an ELO rating, and a zero-sum game is when two people are playing against each other and one person's win is the other person's loss. In the world of zero-sum games, we talked about how it could be represented as ELO ratings, which means there's like a distribution for Warriors' ability and a distribution for the opponent's ability. The Warriors will win if their ability was greater than their opponent's ability. Forgetting all the context and just leaving ourselves with this, we've got what's the probability that one random variable was greater than another random variable? When we hit this in class earlier, we punted. We said we don't have the mathematical sophistication to solve the probability that one random variable is greater than another. So instead we just solved it by sampling. We would just sample different pairs from the two random variables, and then we would estimate the probability that one was greater than the other. That's not ideal. Now, if I knew how to add random variables, one of the ways that we could think about this is we could imagine rearranging this so it's addition. It would be nice if we could solve problems like this. So that's our motivation. We'd like to be able to add, and adding will allow us to directly solve problems. But then I gave you this hint. Learning this piece of theory is an entryway into a magical world where you're going to see some incredible math. So this will be the first step on a bigger, more beautiful journey. So hopefully now you understand what we want to talk about today. We want to just talk about adding random variables, and hopefully now you're a little bit curious. It's like, yeah, I want to know how to random variables. I want to go on a magical journey with all my friends in CS109. Well then come on in, let's go learn. A little bit of review, because we will build on some older concepts we've talked about. Remember at the very beginning when we were learning about probability, we talked about what's the probability of sum of two dice being 7. And in this wonderful space of equally likely outcomes, you could just count. You could think about all the outcomes, and you could think about, here's all the outcomes where the two random variables added up to 7. On some level, this is a precursor to thinking about adding random variables. And I just want to remind you of this example before we jump into the more general case of adding random variables. And the key thing to recall is that, if you think about all your random variables adding up to 7, you kind of make a grid of all the outcomes. And the cases where they add up to 7 would be discrete selection amongst this grid. You could say 6 and 1 adds to 7, 5 and 2 adds to 7, 4 and 3 adds to 7. And luckily, because these are equally likely, we could just then do some counting. Okay, and that's all we've got for review. Now, we just talked about the sum of 2 dice. And we know what happens when you add 2 dice. And we know the probability that it adds to 7. We could also figure out what's the probability that it adds to other things. So if we define y to be a random variable, which is a sum of 2 dice, we now know how to answer the question, what's the probability that y equals 7? We could also answer the probability that y equals something else, like 6. And if we really wanted to, we could solve this generally, and we could figure out the probability that y equals I. And this is special. If you can tell me for any value of I, the probability that y equals I, then you understand this random variable completely. So, assuming that all of your dice are IID, which they are, 2 dice are independent and they have the same distribution. So we have these 2 IID dice, we're adding them together, and I want to reason about the sum. And we could bump this up a notch though. Like we've thought about 2 dice before in class, but we could easily make this 3 dice. We could say, let's sum up 3 dice and see what the sum is. I wanted to show you what the random variables you would get if you thought about adding 1 dice, then 2 dice, then 3 dice. This is ridiculous. This is adding 1 dice. You roll 1 dice and you add it to itself, and you're left with this probability distribution over your values. You could get anything from 1 to 6, and the probability is the same for all of those. How about the sum of 2 dice? Well, we've seen this before. The probability of the sum of 2 dice, the chance of getting 2 as a sum, if you roll 2 dice, is just 1 over 36. The chance of 3 is 2 over 36. And we could work this out using counting in the same principles we had before. Are you curious what the sum of 3 dice look like? So I've never showed you, but you guys want to see? Oh, look at that. Ooh, I heard somebody go, Why is that kind of interesting? It looks kind of normal. Yeah, it looks kind of interesting. Well, that might be just a coincidence, but who knows? And what happens if you sum 50 dice? Oh, that'd be really interesting to think about. Now, actually, do you guys want to see the sum of 50 dice? Oh, let's go find it. Code. Sum of rolls. Okay. Now quickly, I'm going to 100,000 times I'm going to run an experiment. And in this experiment, 50 times I'm going to roll a dice. I'm going to come up with a total sum for 50 dice, and that will be returned from run experiment. Getting a random dice will either give me 1, 2, 3, 4, 5, or 6 with equally likely outcomes. And then when I'm done, I'm going to plot it, just using a histogram. Sound fun? CD sum of variables, Python sum of roles. Here we go. Oh, TQDM is so cute. Yeah, isn't that quite interesting? Huh. Okay, well, we'll just leave that and think about it. Anyways, but the point isn't, we haven't gotten to the theory yet, but you guys understand the problem. We're thinking about adding up random variables. And of course, you have to understand the problem before we get into the theory. And we can talk about adding 2 random variables. We can talk about adding 3 random variables. We could think about adding 50 random variables. And so far, actually, one of the few insights I want you to have is when you add random variables, the result is another random variable. It is another value which will take on different numbers probabilistically. Okay. I have a thought experiment, and it will get us towards the theory of how you can think about adding two random variables in general. Here's the thought experiment. Imagine there's two people, and they're playing a game where they each get points. They'll get points between 0 and 100, and importantly, this is not an interesting game like basketball. It's a game where they all go off on their own and independently get points. So my points is unrelated to my opponent's points. But there's 100 points. And the interesting thing is, let's say I know the probability that player 1 gets 0 points. I know the probability that player 1 gets 2 points, 3 points, 4 points, any value of little x between 0 and 100. And I know the same thing for y. They could be two different probability distributions, but I have the probability belief of x getting on points and the probability belief of y getting different numbers of points. And then I ask you the question, what's the probability that these two people tie? Now let's just review. Their scores are independent. And for any score, I can tell you the probability that x gets that score and the probability that y gets that score. So hopefully this thought experiment is something you can think through, but I'm going to give you a minute just to think about it with your friend next to you. So how are you going to get this probability? Okay. Now, this doesn't seem that important, but if you can get this logic, it's halfway towards getting the logic of what happens when you add two random variables. So this isn't about adding random variables. This is talking about the probability that two random variables take on the same value. And importantly, these random variables are independent. So if this is player X's score and this is player Y's score, what's the probability that they tie? And you can think about all these different mutually exclusive cases. For example, there's the case that they tie and they both got 80 points. There's also the case that they tied and they both got 79 points. There's the case that they tied and they both got 81 points. And if you think about all the little values I, which are the points that they both get, since all of these cases are mutually exclusive, you should be able to just add them. So my claim is that the probability that these two people tie is the sum over all the values of points that they could get, the probability that x gets exactly those points and y gets exactly those points. So this is going to be mutually exclusive cases, so we can add them. You can't both have x equals 5 and also have x equals 6. Mutually exclusive, so you can add them all. And this is, in this world, they both have I points, therefore they tie. This just gets a little bit nicer in that because they're independent, we don't have to think about these things jointly. We can think about the probability that x equals I times the probability that y equals I. Yes, question?
You don't have to think of them jointly, because I would always assume that you can.
You cannot always, it's a good question. You can't always do this. Let me see if I give you an example. Let's say that, any two things that are not independent. I don't know, if the first thing is like you get a 1 on a dice and the second thing is that the sum of the two dice is like 12, then it's not the probability that you get a 1 on dice times the probability that the two dice sum to 12. Even though there's non-zero probabilities of those things happening, they can't both happen at the same time. This property is only true if they're independent. Good.
I don't know if to help maybe it's like a homework question where we have to get the zones.
Yes. Yeah.
Does that help me, like, whether you can't always do it?
Yes, exactly. So Any case where they're not independent, you can't do this. You'd have to think about them jointly. But if they are independent, then product of and, or probability of and becomes easy. Follow up? Yeah.
Is there a way for us to visualize this using the graphs? Like, can we see like how much do the two distributions overlap? And is that a sign of how much they're going to be attached?
Yeah, you know what would be a little bit easier than if you looked up their probability mass functions on their own? Would be if you looked up a joint table. And if you look up a joint table, you know, if you look up 0, 0, let's say this is for x and this is for y. This cell here is the probability that x equals 0 and y equals 0. And so what you're really going to have is, this thing is going to be all the values in the diagonal summed together. So you can see how maybe if you made it color-coded and darkness means whether or not there's high probability, you know, you could visualize how much weight there is on that diagonal. Good question. Okay, good? Yes?
What would Bayes look like in the first one? So in the case where to find x, y, we'd have to sort of convert it to an equation. So x given y given x, what would that look like? In the case where they weren't independent.
If they're not independent, then I would probably break, So is Bayes going to help you? I guess you could, If you just had one of these terms, you could use law of total probability, which has a bunch of conditionals in it. But I think with both those, I can't think about how Bayes would help. That might be a limit of my own imagination. Because Bayes is helpful when there's a conditional. If there's a conditional, you can flip it. Law of total probability is helpful if you want to like go from, you know, this joint to knowing one of these on its own. But here, independence is the most helpful thing. Let me think about this more. You can come talk to me afterwards, because I might be missing something. It's very, very possible. Okay. More ideas? Okay. So as I said, that's not the thing we wanted to get to. That was just a warm-up. The real question we want is, we have two random variables, and let's imagine they could be independent or they might not be, and we want to think about the probability of the sum of those random variables, and we want to think about the whole probability mass function of that sum. And if you want to think about the whole probability mass function of any random variable, you have to give the probability of that random variable taking on the value n. So the random variable we're thinking about is the result of adding x to y. That gives a random variable. And if you can tell me what's the probability it takes on n for any possible value n, you have told me what happens when you add these two random variables. Sound good? Okay. Here is the idea. We're going to do something very similar to what we did with the tie. We're going to think about many different cases that lead to these two random variables taking on a value n. Here's one case. If x takes on the value 0 and y takes on the value little n, what's the sum of those two values? Yeah, great. If x equals 1 and y equals n minus 1, what's the sum of those two values? N. Okay, you guys are very good at this. I bet you can get this next one. What about 2 plus n minus 2? Oh man, all these are different cases where these two random variables add up to n. And my claim is this is all of the cases. My next claim is they're mutually exclusive. And then my final claim is they're countable. You know, you can have an index starting at 0, and that will be the value of x, and it can go up till n, and that will be the value of x. And the value of y is always going to be whatever x is, or n minus whatever x is. So do you guys first believe my claim that every row here adds up to n? Now do you believe my claim that they're mutually exclusive? Mutually exclusive means you can't have two rows at the same time. And that makes sense because x can't be 1 at the same time that it's 2. And then the final claim I make is that this covers every possible way that you could get n if they're discrete. And I guess if they're taking on whole number values. Okay, as such, every single one of these, we can talk about the probability that it happens. This is the probability that x equals 0 and y equals n. This is probably that x equals 1 and y equals n minus 1. This is probably that x equals 2 and y equals n minus 2. And therefore, adding two random variables leads to this very nice equation. What's the probability that x plus y equals n? Well, let's loop over all the different ways that they could add up to n. There is x equals 0 and y equals n. There's x equals 1 and y equals n minus 1. This sum is basically just expressing the addition of all these mutually exclusive cases. And this could be the end of your story if you're talking about the addition of two random variables that are dependent. If they're dependent, then you have to think about the joint probability together. If they're independent, though, this isn't the end of the story. If they're independent, then this can end up being the sum from I equals 0 to n of the probability that x equals I and the probability that y equals n minus I. Oh, sorry. If they're independent, though, this will become a product of probabilities. So the probability that x equals I times the probability that y equals n minus I. If they're independent, you can set up this equation. In this equation, you only have to think about the probabilities of each random variable on its own. Independence makes things a lot easier. You don't have to think about random variables jointly, probabilistically. You can think about them one at a time. Okay. So, just putting that into slides, these are the two different rules for talking about adding random variables. This is the general case where they might be dependent, and this is the general case where your two random variables are independent. Now, we're not going to go too deep into this in CS109, but I do want to give you the insight that this will scale nicely if you got to something like a continuous random variable. If you want to talk about the sum of two continuous random variables, this sum will just become an integral, and these will just end up being densities. But we're going to stay in the discrete world for CS109. So, in some way, we could have used this to derive the graph for the sum of two dice. Now, we did this using counting, but we could have used this rule. And this rule says the probability that x plus y equals n is, well, the sum over all the different values that x could take on and the value that y could take on that allows the two things to be equal to 1. Now, first of all, the probability of any two assignment of dice, like x equals 1 and y equals 2, it's 1 over 36. No matter what dice combination you have, there's one outcome out of 36. And then the one thing that's going to change here is the bounds. You know, it must be the case that whatever x is assigned to has to be between 1 and 6. You can't say x is 0 because it's a dice, and dices can't be 0. And the same thing with y. Y can only take on values 1, 2, 3, 4, 5, and 6. So this exact same equation, if you have probabilities of 1 when these things are both values between 1 and 6, and 0 otherwise, probability of 1 over 36 when these are both valid assignments to dice, and 0 otherwise, you end up with this very beautiful chart. This is just the plotting of that equation. So at this point, you guys now have a general rule for adding two random variables. No matter what two random variables are, you could apply this thinking. And actually, you now know how to do this thing called convolution. Back in the day, this lecture used to be called convolution. Do you know that convolution is just a really fancy probability way of saying adding two random variables? It's like whoever talked about adding two random variables for the first time couldn't just call it adding two random variables. They had to call it convolution so they could feel really fancy. But anyways, if you see convolution, you should just translate it into two things. They're talking about adding random variables and they feel very fancy. Sometimes adding two random variables doesn't require you to go all the way to this origin story of adding two random variables. Do you guys want to hear about some cases where adding two random variables is easy? Okay, here's a case where adding two random variables is very easy. You have two different binomials. They have different values of n, but they have the same value of p. And even without going to the origin story, you can think about what is the sum of x and y. And do think about it. Meditate on it for a little moment. What happens if you take one binomial? That's the number of successes in n1 trials. You take another binomial, which is the number of successes in n2 trials, and you add up those number of successes. What will the result be? It won't be a constant. It will be a random variable. And sometimes we call that random variable z. And if you add up those two things, what is z? It's a binomial. But what are the parameters of the binomial? Well, z is number of successes in a bunch of trials. Every trial has probability p of success, and there's n1 plus n2 trials. And that comes from it semantically, like x is number of successes in this many trials with probability p. Y's number of successes in this many trials with probability P. If you add those number of successes, it's equivalent to if you ran N1 plus N2 trials, each with the same probability P. So if you add up two binomials with the same parameter P, you're in a good place. Yes?
You write n1 and 2 high because you're going to divide it by something?
No, just for suspense. The question was, did I write N1 plus N2 high because I'm going to divide by something? No, that is just poor typography on my part. Does this feel better? Okay. Yes?
Can we accept that every sum of random variables is another random variable?
Yes. Do you want me to repeat that? Or? Yes, that is the case. If you take two random variables and add them together, always a random variable, because that result of the sum, it's not deterministic. It will vary. There will be probabilities to the different values we'll get because there's probabilities to the thing that goes into the sum equation.
Is it possible that if we add two random variables that have the same model, will that random variable will still follow the same model?
Not always. Not always. And I'll give you a quick example. Uniforms. You add two uniforms, you don't get a uniform. What do you get if you add two uniforms? Interesting mystery. Well, we'll get there, I promise. But right now we're adding two binomials, which is a good time, because if you add up two binomials, you just end up with another binomial. Not everything will be so beautiful. Thank you, binomials, for making our lives easy. And the intuition is exactly what we described. You know, x1 had n1 trials, y had n2 trials, so z has n1 plus n2 trials, all with the same probability of success. Now here's a cool one. What if you tried to add up not binomials, but normal distributions? And there's this beautiful property of normal distributions. If x and y are two normal distributions with different means and different variances, it turns out if you add x and y together, you will still get a normal. Now, this is not always the case that if you add two random variables, you'll get the result being the same distributional type. And normals turn out to be exquisitely special because it doesn't matter about the parameters. You can always add two random normals and get another random normal back. And not just any random normal. If you add up two normals, you'll get a normal back, and its mean will be the sum of the means, and its variance will be the sum of the variances. You may ask for me to prove that, and I think that is a very good question if you're wondering, but I'd say hold on to that idea till we get to this more general result from adding random variables. Does that sound good? Okay. You can take this to like nth degree. Instead of adding two normals, you can add n normals. And no matter how many normals you add, it will lead to another normal, and the mean will be the sum of the means, and the variance will be the sum of the variances. So that's a lot of fancy notation which says no matter how many normals you're adding together, you still end up with a normal, with very predictable mean and variance. And I have a final one that's nice for you guys. What if you have two Poissons? So Poisson x happens at rate lambda 1, and Poisson y happens at rate lambda 2. X and y will represent number of successes at their respective rates in a fixed time interval. If you add up those number of successes, you still get a Poisson. And the rate of this Poisson will just be the sum of the previous rates. And that is something that we could prove, and I think there is a proof for that in the course reader. But I want to first take a step back, because we've got three useful rules I just gave you, and I want to practice using them. So the useful rules I gave you is the sum of two binomials, the sum of two Gaussians, and the sum of two Poissons. Particularly the sum of two binomials, they had the same parameter p. The sum of two Gaussians could be any parameter, and the sum of two Poissons could be any parameter. And then I ask you this question, and I want to see if you guys can figure it out. Say you're working with the WHO, you're planning a response to initial conditions of a virus. There's two exposed groups, and you want to know the total probability of more than 40 infections. In group 1, 50 people were exposed. They each are independently infected with probably 0.1. In group 2, 100 people are exposed, and they're independently infected with a different probability. In group 2, you had a higher probability of becoming infected, and that was 0.4. And we want to think about the probability of more than 40 infections. And I'll get it started. You can say the number of people infected from group 1 is a random variable. You can say the number of people infected in group 2 is a random variable, and what we're really interested in is the sum of those two random variables. But then there's a puzzle for you guys. You know, if you think about it, this should be a binomial, and this should be a binomial. can you reason about the sum of these two binomials? Why do it in your heads when you could do it with the person next to you? So give it a shot, think about it with the person next to you, because this is a classic example of what a problem on a problem set could look like with the sum of two random variables. Okay. There's many paths to answers here. There's one path to be avoided, and then there's two happy paths that will get you the right answer. So, I don't know, let's throw up some ideas. I got bored, let's brainstorm.
So I was thinking that if you said the probability that x plus y is greater than 40, then that's 1 minus the probability, that 1 minus the sum from 0 to 40, that x plus y equals I.
Mm-hmm.
And then since we know that formula from before, x plus y equals n, we can substitute that in.
Yes. So one strategy is, we have this formula. We think the values of x1, which is the number of people infected in group 1, is independent of the number of people infected in group 2. They're two random variables, but they're not influencing each other. And we could use this fundamental definition of adding two random variables. So we can think about the probability that x1 equals, like if you want to say, like, what's the probability that the sum of two random variables is 0? Well, that's probably that x1 equals 0 and x2 equals 0. If you want to know the probability the sum of two random variables is 5, then we have to think about looping from x1 equals 0 up till 5, and x2 is equal to whatever the complement is. This first principle approach will 100% work. But there's another way. And there's a question or an idea.
Oh, I just thought that we could convert the binomial, we could approximate it to a Poisson, and like lambda is Pn. So in the first case, for every 50 people, it would be, lambda would be 5 for 50 people. In the second case, it would be like 40 for 100 people. So basically, you convert the first case into 100 people as well.
Yes.
And then you just add the two Poissons.
So many things that I absolutely love and I want to deconstruct it. First of all, you said approximate the binomials. And there's something very special about that insight. Before you even get there, you might think, hey, don't we have a rule for adding two binomials? We've already talked about what happens if you add two binomials. You get this thing. I said adding two binomials is easy. You just add up the number of experiments. But why did you want to approximate? Why didn't you want to just use this equation?
Because P is different.
Ah, P is different. This simple equation I gave you for binomials only works if P is the same. Therefore, you thought, I'm going to use approximation. And then you thought, I'm going to use a Poisson approximation. Everything you said after, I'm going to use a Poisson approximation was correct, right? All those ideas for how you would get lambdas. But the only problem is, Poisson is meant for extremes. Extremely large n and extremely small probabilities of P. And I could argue that this is extreme, but since probability 0.4 isn't that extreme, your Poisson approximation here will be okay, and you'll get a pretty good answer, but it won't be that tight an approximation. But let's plus that answer. Let's take that answer and think, okay, if Poisson's not extreme, if this isn't extreme enough for Poisson, who can play if we want to play the approximation game? Yeah?
Use a normal approximation and then solve to the formula we discussed in the previous slides.
Binomials can be approximated by Poisson or normal. So you could say that I will get the approximating normal for this one. I'll get the approximating normal for this one. And normal approximations are happy, when everything looks moderate. The variance check that we gave you works out for both of these numbers, and it turns out a normal approximation does work. Now, both of these were good paths in that there's an easy way to add up Poissons, and there's an easy way to add up normals. So if you can turn your binomials into one of these worlds, we can think about convolution. Yeah, question?
So I have another approach.
Oh yeah, fantastic, okay.
I was thinking of doing almost like a summation within a summation. So I was thinking back to the table that we had earlier.
Yeah.
With all with n minus I things.
Uh-huh.
And then you have you start by n is equal to 40. And then you go n is equal to 41, n is equal to 42, so you sum through n is equal to 40, and then you add to that the sum through n is equal to 41.
So somewhere in here, there's the line, and it'll actually be a zigzag because they're discrete. And at this line, if you take y's value and x's value, it sums to 40. This is like sum to 40 line. And your insight is, if you want to know the probability of more than 40 infections, then you can just add up all the probability mass over here. And you can figure out what's the probability of every single grid in this, and that would also work. Okay, I love it. I love it. These are many good approaches to solving this problem. Now, the first question I just have is, should we use the binomial sum of random variable shortcut? And hopefully at this point you're like, no, that binomial sum of random variable shortcut was only when p was the same. Yeah.
How do we see that it's easy to add up Poissons? This seems non-intuitive.
You could actually work it through. So Poisson is one where we can actually go to this first principle definition. And if you say they're independent Poissons, and you think about these probabilities, if you put in the probability mass function, you will be able to factor it into a new Poisson. That's a cool question. It is unintuitive. Why don't I show you the proof? Okay. So.
Is that fact true more deeply because Poissons are emerge from Poisson processes?
There's two ways to think about it. Mathematically, if you did that first principle thing, you end up with another Poisson. And the other way to get it is to think, yeah, Poisson processes mean these independencies, and also there's this convolved rate, and you could get into your head about it, but I believed the math when I saw it. Okay, if you wanted to go down the path of the normal approximation, this is what it would look like. Instead of just having A, which is the true binomial, and B, which is the true binomial for group 2, I had approximating normals. I say x is my approximating normal, and you can figure out what that is. It turns out mean is 5 and variance is 4.5. And y can be approximating normal for the second group. Mean is 40, variance is 24. The probability that the sum is greater than 40 is the probability, or is very similar to the probability that the sum of your normals is greater than 39.5. 39.5, what happened to that half a person? Yeah, sorry, pal. Continuity correction, you're out of here. It's not actually half person missing. That's just because we went from a discrete and we approximate with a continuous. And whenever you do that, you have to think about half a unit and which direction you have to include. So this is very similar to the question, what's the probability that the sum of these two normals is greater than this value? If I call my sum of two normals W, that W will have a known distribution. You just add up the means of the two normals you summed, and you add up the variances, and you get a new probability distribution W, which is in fact a normal. And if you want to ask the probability that W is greater than 39.5, that's asking what's the probability that this normal is greater than 39.5? Oh, I switched from W to X, how embarrassing. But anyways, it's 1 minus the CDF at 39.5, and you can just plug that in either through the 5 formula, or you could use the SciPy CDF. Cool. Yes?
So how do we get the 5 and 4.5? How do we get the parameters of the normal from just the lambda? So from the n and p values that we have of the binomial.
It's a very good question. Okay, and I'm going to switch these to W's. How did you get 5 here? The idea is, if this is a binomial, and this is the approximating normal, you should choose the mean here, which is the same as the mean of this binomial. What's the mean of a binomial? Well, that's its expectation, which is, if you look up the formula, n times p. And 50 times 0.1 is 5. What's the variance of a binomial? It's n times p times 1 minus p, which will be 5 times 0.9, which is 4.5. So that's how you figure out the matching values for mean and variance if you're doing your approximating binomial. Okay. Now, I showed this to some students, and people went away happy, and then one student came back very unhappy. He says, Chris, there's a contradiction in two things you've told me in CS109, and I cannot sleep at night. Can we talk about it? And he posed this question to me. He said, imagine x is just some normal, and I'm going to add x plus x. There's two ways of thinking about x plus x. You can think about it as the adding of two random variables, or you can think of it as x times 2. You know, whatever x value is, I'm going to multiply it by 2. Earlier in class, you said if y is a linear transform of a normal, you'll end up with another normal, and I gave a way of talking about what that other normal will be. Particularly, I said, if y is equal to a linear transform of a normal, take that normal, take the constant, and multiply the mean by the constant. And then the variance will be multiplied by that constant squared. So I said this earlier in class. But now I just told you how to think about the sum of two Gaussians. I said, you know, if y is equal to x plus x, you can think of this as the sum of two Gaussians. And I just told you, if you add two Gaussians, you'll get another Gaussian. Well, that doesn't seem to contradict yet. And the mean will be the sum of the means, and the variance will be the sum of the variance. And you're left with this. It looks so similar. Through these two different approaches, both of them lead you to conclude that the sum of these two Gaussians is normal. And both of them lead you to conclude that the mean of this sum will be 2 times whatever the mean of x was. But they have different answers for the variance. And the student couldn't sleep and came and was like, there's something wrong in the world of mathematics. This is like, does this go deep? Is there something wrong with addition? 2, are you lying to us? And the answer is no. There's just one really interesting, subtle point here. And it's worth talking about because it's an assumption that we've made. Suspense. Oh, I'm not going to tell you. You're going to tell me. Yeah. Sorry?
Are they supposed to be independent?
Well, are they? Here, x and x. Are they independent?
No.
That's it! Now, x is not independent of the same random variable x. If you see x plus x and there's the same random variable, what this implies is, like, roll your dice for x, get its value, and then add that exact same value to itself. So if like x turns out to be 4, then this is also 4. You end up with 4 plus 4. X might turn out to be 5, then you get 5 plus 5. But no matter what, this and this value are the same. That's why we could write it as equal to 2 times x. But therefore, if I know the value of x, does that tell me anything about the value of x? Yeah. They're not just missing independence. They're completely dependent. And the sum of two Gaussians rule that I told you assumed independence of the Gaussians. The sum of two Poissons that I told you assumed independence, and the sum of two binomials that I told you assumed independence. Okay, cool. Moving on. So anyways, so now we can all sleep at night, and there is a bug here, which is that x is not independent of x. Very good. Okay, let's go back to zero-sum games. So I promised that we'd be able to think about the probability that the Warriors win in a zero-sum game. We've already talked about how this can be represented as ELO scores. You can think about every team as having an ability, and it's drawn from a normal distribution. The mean is like how good the team is, and the variance depends on the sport in the original ELO paper, and they set basketball to be 200 squared. The idea is that both teams, when they play, they're going to sample from their ability distribution, and whoever has the higher sample ability wins. This is the theory of ELO. It's not actually how basketball works. They actually play a game with a ball and 2 nets. And then we ask the question, what's the probability that the Warriors win? And we've talked about how this is before is, well, we think about the Warriors' ability random variable and the opponent's ability random variable. And this is really asking what's the probability that the warriors pull a value that's greater than their opponents. And to give you plots for what this could look like, the warriors have a random variable. It could look like this normal. The opponents have a random variable. It could look like this normal. We're asking what's the probability that this random variable is larger than this other one. My claim for you is that this is an addition question. Asking if one random variable is larger than another is the same as addition. And you're like, what? That doesn't sound like addition. It sounds like inequality. And just to be clear, like if we say that this random, what's the chance that this random variable is larger than this one? It says this random variable will take on a value. Let's say it's this. And this random variable is going to take on a value. And it could be this one, but that's very unlikely. More likely, it could be something like here. And we can think about what's the probability that this value is greater than that one. And I claim it's addition? Insanity. Okay. Here is why it's addition. I give you your two normals for your two random variables. I ask what's the probability that one random variable is greater than the other. And then my next claim is this is the same as if you were subtracting one random variable from both sides, you get what's the probability that the difference of these two random variables is greater than 0. So hopefully at this point you believe that the probability of one random variable being greater than another one is actually a subtraction question. It's probably that the subtraction of two random variables is greater than 0. But if you recall, if you take a normal distribution and you do a linear transform, like you take that random variable and multiply by, say, -1, you'll again get a normal. That -1 will be multiplied by the mean, and the variance will be multiplied by -1 squared. So negative of the opponent's ability will be this Gaussian. And if you add up this Gaussian and this Gaussian which we just derived, the sum, because they're independent, will be another Gaussian. And we can get the probability of the difference between AW and A0 as a random variable. You'll add up the means. The mean of AW is 1797, and the mean of negative AO is -1555. We add those two numbers together, you get 242. You add up the variances, and both of them have variance of 200 squared, so adding up the variance will give you 2 times 200 squared. And now you can ask, what's the probability that this difference is greater than 0? And it'll just be equal to 1 minus the CDF, and that's something you could look up. And you can end up with the probability of 0.804. Before we had to sample to get this answer, and now we don't need to. Okay. Okay, the convolution will not be televised. Okay. Now, I want to mention quickly that it's not always so rosy. We've talked about binomials. Sum was so nice if they have the same p. We talked about normal. If they're independent, the sum is so nice. And Poisson, if they're independent, the sum is so nice. And you may be like, sums are always going to be so beautiful. And I just want to, for a moment, look at the scary world of how this can all fall apart. Uniform. So, just really quickly, I hope you believe me, that, but if you wanted to talk about the sum of two discrete random variables, we had this formula. So the probability that the sum comes to A is just going to be A minus, or the probability that one of the random variables equals whatever you're looping over, and the probability that the other random variable equals your target minus the index. And there's a continuous version too. And in the continuous version, it's the exact same thing. It's just become a sum, becomes an integral, and probability mass function becomes probability density. So what happens if you add our good friend, a uniform between 0 and 1, with our other good friend, a uniform between 0 and 1? Just to be clear, these are the two uniforms that we're trying to add together. So we're trying to add two uniforms. They both have probability density that are equal to 1 in the range 0 to 1. And if you think about it, you could ask the question, if x is uniform and y is uniform, and particularly we're going to say they're uniform with 0, 1, what's the probability that x plus y, and this should be density, what's the probability that x plus y is equal to some number, and we could say something like 0.2 to start out with. Of course, we're going to want to think about this in all the different cases. But what is the probability that the x plus y is equal to 0.2? Yeah.
0.
No, it could happen. Oh, well, the probability density. Good point. Okay, so the probability is 0, but the probability density is going to be non-zero. And the claim, the continuous equivalent of this is that it's going to be the integral over some loop, and we'll think about its bounds in a second. And this will be the likelihood that x equals I and y equals 0.2 minus I. So we're going to integrate. We'll be like, what's the chance that x equals 0.1 and then y also equals 0.1, because then they would sum up to 2. Now the nice thing is, both of these values are 1s. If you look at the PDF value of both of our uniforms, it's 1s. So it feels like we have the integral of 1. The tricky thing is to think of what are the bounds on I such that these two things don't give you 0. Because if you ask what's the probability that your uniform is less than 0, it's 0. And your probability that your uniform is greater than 1, that's also 0. So what bounds are going to make both of these non-zero? Well, I'll tell you what. From this one, we know that I has to be greater than 0 and less than 1. Because if I is between those two values, this is just 1. Otherwise, it's 0. And 0 multiplied by 0 is 0. So I already know that I has to go from 0 to 1 for this value. But how about this one? This is super tricky bound work, but if I takes on the value 1, what is 0.2 minus 1?
Negative 0.8.
It's a negative number. And what's the density of our uniform at negative 0.8? It's like asking what's the density over here. It turns out if I gets too large, this thing will exit the range of being in the CDF of y, one of our uniforms. So the bound over here, what's the biggest value that I can be such that this doesn't exit the range of being 1? Yeah, if it ever becomes greater than 0.2, then this will become a negative number and you'll get a density of 0. If it's between 0 and 0.2, then this will be a number that is positive and less than 1, and this density will be 1. So in this range from I equals 0 to 0.2, you end up with 1 times 1. So this will be equal to this density, di in this case. And if you did this integral, it would just end up being 0.2. And this is looking pretty good. You're like, oh, that doesn't feel so bad. If you want to think about this, you could think about different points. We just thought about point 2, and we found out that the density, that the sum of the two uniforms is equal to 0.2 is equal to 0.2. And you can try a bunch of these points. If you did it, you'd realize that the answer is piecewise. In fact, if you're thinking about the sum of two uniforms being up to 1, it just linearly increases. As we ask, what's the probability the sum of two uniforms is 1/2? It's 1/2. What's the probability the sum of two uniforms is 3/4? It turns out to be 3/4. For a very similar argument to here. But then after you get to 1, then your bounds work changes and it starts to go down. Now you could do all that work piece by piece. It just turns out that the uniform, if you add two uniforms, you certainly don't get a uniform. Instead you get this weird triangle thing. So the sum of two random variables isn't always a clean answer, and uniform really drives that point home. The other thing to note is, if you want to think about the sum of two continuous random variables, it'll be just what we talked about before, just with integrals and densities. Now I want to point out one cute thing. Remember we talked about the sum of two dice? And dice are quite similar to uniforms in that they're equal probability of every outcome. And you got the sum of two dice looks like this triangle. And now we have the sum of two uniforms. Looks like that triangle. Is there a conspiracy going on? Question.
Should the shape of the triangle change based on the bounds of the uniforms?
Yeah, if you had not 0 to 1, you would end up with different bounds work over here and you get different shaped triangles. Still a triangle though, suspicious. This is where they hide the treasure. No, okay. But then you might wonder, what happens if you add up 100 uniforms? And the beauty is we can do this. We've got computers. If we wanted to not just think about the sum of two uniforms, what if we wanted to think about the sum of 100 uniforms? If I wanted to do this, what I would probably do is I would set up this code. And in this code, I would run 10,000 experiments. Every experiment, though, I'm going to sum up 100 uniforms. I'm going to get a list of all those sums, and then I'll plot the histogram. Does that sound like a cool thing to do? So every experiment, I do exactly this. I do convolution of 100 uniforms. So we know that the sum of one uniform is just this. So the sum of one uniform is just that. We know the sum of two uniforms is just that. What is the sum of 100 uniforms going to be? Oh, I don't know. But we can be experimentalists. And we can go to sum of variables. And we can do Python 3.9, sum many unis. Here comes the suspense. It's going to do this 10,000 times. TQDM is so nice. It does this like really cute bar. Check it out. It's not that important right now. What is important is we're getting really close to seeing our answer and your hypothesis. Oh, wow. It was pretty skinny, but when we readjust it, what does that look like?
Gaussian.
What? Maybe there is a deeper mystery. Maybe there is a conspiracy all along because we added up dice and we got a Gaussian. And then we added up uniforms and we got Gaussian. And now you're thinking there's something special about dice and uniforms that gives you Gaussian. And at this point you're like, I've gone crazy, but I'm still going to do it. What happens if I add up a lot of beta distributions? So we learned about beta distributions yesterday. You know, they don't look like uniforms at all. Instead, they look like these little bumps that represents distributions of probabilities. That's not important right now. I'm going to think about adding 100 betas together. IID betas. So they all have the same distribution, and they're all independent. I'm going to add 100 to them. I'm going to do it 10,000 times, and we're going to find out what happens if you add up betas. You guys ready? There it goes. What do you think? What do you imagine happens if you add 100 betas? Beta's a weird thing to think about. What's convolution going to be? I don't know. Maybe it's going to look like another beta? Yeah, it could be another beta. Something is weird in the world of probability. Oh, it turns out if you did 100 Poissons, the same thing happens. Like, trust me, if I were to do the same experiment, replace the beta with the Poisson, again, you would see something that looks like a Gaussian. Now let's have our moment of silence before we present one of the most beautiful results in an entire history of probability theory. A result that's profoundly important as it is profoundly beautiful. The central limit theorem. This is not a coincidence. There is something beautiful and magical in our world. And this beautiful and magical thing in our world is no matter what random variables you have, if they're IID, if you add up enough of them, they always converge to a normal distribution. Betas, uniforms, Poissons, just your friend's random variable that they drew on a graph. If you draw enough samples from that random variable in the graph and you add them up, the resulting random variable will be a Gaussian. And not just any Gaussian. If you add up IID random variables, no matter what they are, they could be Gaussians, betas, your friend's distribution, you'll get a normal. And the normal will have a mean which is equal to the mean of the underlying random variable it's drawing from, times by how many experiments you ran. So if you added up 100 uniforms, this will be 100, and this will be the mean of your uniform. And the variance will be 100 times the variance of the uniform, or replace uniform with whichever distribution it came from. IID is important, so the sum of n IID random variables is normally distributed with a calculatable mean and variance. And it's beautiful, and it's gorgeous. And I could talk about how beautiful and gorgeous this is in so many different ways. One way to talk about it is it explains why we saw this. Sum of one dice roll, uniform. Sum of two dice rolls starts to look like a triangle. But you sum 3 dice rolls and already it's starting to look like a normal distribution. We can go deeper into the proof. In fact, I will share that video that one of the personal challenges back in the day, and that goes over the proof for why this is true. But to give you an intuition for why it's true, when you add 2 dice rolled together, why is there more weight in the middle? Because there is more ways to get a 7 than there were to get a 2. And when you add 3 dice rolls together, the same thing happens. There's just way more ways to get something close to the average value on a dice times 3 than there are to get things that are in the extremes. So that starts to give you some intuition, but I'll give you that YouTube video if people want to go a little bit deeper. It explains so many things. It explains why, when you have a binomial and you look at its distribution, it looks like a Gaussian. That wasn't a coincidence. That wasn't a hack. It comes straight from the central limit theorem. Why does a binomial always look like a Gaussian? Because a binomial under its hood is the sum of independent random variables. You're like, which independent random variables? I thought a binomial was just a binomial. No. A binomial is so much more. If I say you have a binomial, so x is a binomial, with n equals 100 and p equals 0.4, or 0.5, let's say, my claim for you is that x is the sum of IID random variables. And particularly, x equals the sum from 1 to 100 of yi. And what is yi? Yi is a single Bernoulli representing a coin flip. So yi is your Bernoulli with 0.5. So if yi is a single coin flip with 0.5, these are IID random variables. And the sum of IID random variables will always be well approximated by a normal. That binomial approximation by a normal comes from the central limit theorem. Yes?
Oh, no,
Okay. We got to stretch part 2. Anyways. We talked about, okay, so the sum, the approximation of binomial from a normal comes from this deep idea that we have on the board. It's that the binomial itself is the sum of Bernoullis. And particularly, if you thought about it through the central limit theorem, it'd say that the good approximating normal would be equal to n times the mean of your Bernoulli. But the mean of a Bernoulli is just p, and the variance of a Bernoulli is just p times 1 minus p. And you end up with the exact same approximation, whether or not you use the central limit theorem or you use our normal approximation idea from before. And just to drive this home, this is a random variable. It doesn't have a nice equation. Instead, it has a probability mass function defined by like some crazy person just drawing a plot. But if you took samples from this and added them together, you would end up with the sum of IID random variables. So if you took 15 samples from this and added them together, you would get something where the sum is distributed as a normal. And that's just driving home the point that the central limit theorem doesn't require the underlying thing to be a clean distribution. All it requires is that the things you're adding together are IID. Wow, that's so cool. Fantastic. Whatever. You take this distribution, you add them together, you get a normal. Okay, what a good time. Now we only have 5 more minutes. And it's a Friday and you guys have worked hard. So maybe let me finish this example and then I want to leave you with an idea of why I think this is so beautiful. You might ask the question, how good is the central limit theorem? And to answer that question, one thing I could do is we could take uniforms and we could take the convolution and we could compare it to the normal approximation. If you talked about central limit theorem where you thought of n equal to 2, so the sum of 2 independent uniforms, the true answer is in the dashed line and the central limit theorem is in the orange line. Already, this looks like a pretty good approximation, but there's some error. And you can figure out what's the exact answer, and you could figure out what is the central limit theorem answer. And you can see the central limit theorem would give you a different answer to the question, like what's the probability that this sum is less than, say, 2 over 3? But what if we got to 3? If you add up 3 uniforms, you get this dashed line, but the central limit theorem would say that it's approximated by this orange line. And already, if you start to ask probability questions, you'll get very, very similar answers. And if you bump it up to something like 10, the sum of 10 uniforms is so perfectly represented by the central limit theorem that any probability question you get, you're going to be so incredibly close if you use the CLT. Okay. If there's a major takeaway from today, 1, you learned how to do convolution. You learned how to add random variables. You solved some cool problems with that. We learned some cool tricks. Then we bumped it up a notch and we started to realize that the convolution of many IID random variables always gives you a normal, which is a beautiful thing. Now, if I could, we'll talk about this later, but if the sum of IID random variables is normal, I want you to think, what is the average of IID random variables? Because sum was just one operation we did. You could also think about average. You could also think about a thing called a max. I'm going to leave that for you guys to think about, and we can pick it up on Monday's class. But I want to leave you with a little bit of history and a quote. So if you guys are curious about the history of this comes from Abraham de Moivre. And in fact, he was a refugee who left France because he was a Huguenot who was being persecuted. He ended up going to the UK. Because of that, he wrote the Doctrine of Chances in English. And because of that, UK became the place for Bayes to come up with Bayes' theorem. Like the whole history of mathematics starts from this person being a refugee and having to leave France and therefore not writing the Doctrine of Chances in French. Doctrine of Chances is where the central limit theorem was first shown. He first showed it for a sum of Bernoulli's. It was then taken by Laplace, and he did the first proof that a binomial can be approximated as a normal. And then finally, the precise definition of the general version of the central limit theorem was given by Alexander in 1901. And then, whatever about the Beyonce thing, I'll explain that later. We're going to play a game later. On Monday, we're going to start with a game where we're going to think about central limit theorem. But I would like to leave you with this idea. This is a quote from Galton on the central limit theorem. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the central limit theorem. The law would have been personified by the Greeks and deified if they had known of it. It reigns with serenity and complete self-effacement amidst the wildest confusion of adding random variables. The huger the mod, the more random variables. And the greater the apparent anarchy, the more the variance, the more perfect is its sway. It is the supreme law of unreason. Whenever a large sample of chaotic elements are taken in hand and marshaled in the order of their magnitude, adding, an unsuspected and most beautiful form of regularity proves to have been latent all along. It is a beautiful thing about our universe. Have a fantastic weekend. Come back on Monday, and we'll continue this beautiful deep dive into theory of probability. Thank you very much, CS109.